Hey, I'm Robbie Richmond. If you do not know me, I am the TA for the section that begins at 8:30 in McHenry 125. And I usually do these practice exam breakdowns before the exam, and I think they're very helpful for students who look at the exam information sheet, or not the exam information sheet, the answer key to this exam, and sometimes we don't have work placed on those exams, so I would make these videos and kind of in hopes of to give a student perspective how to succeed on these exams, what I did for each exam, and how I eventually ended this class with an A because that is a requirement for TAing. For this exam, I would make sure that, you know, we know where we're going in our each designated room. We know how the general exam structure is, and knowing that structure, there are some strategies to kind of ensure your success in this exam. Alrighty, so these exams are practically the same. I will say I took this class my freshman year and I'm a senior right now, and this exam one looks eerily similar to the one that I remember taking in my freshman year. You'll always be given an exam information sheet, you'll be given a periodic table, and this will be an exam that will only be, you'll have to use a scientific calculator. If you have a calculator that is a graphing calculator like a TI-84, you cannot use it, unfortunately. So please make sure you have the right calculator, because if you don't have a calculator for this exam, it's not going to be a fun time for you. All right, so just a little bit logistics. First name, please put your first name that shows up on DegreeWorks. Last name, signature, student ID number. Please memorize this. Please memorize this. So you're not like, oh man, I forget, because that did in fact happen to me my freshman year, and that was a little embarrassing. Make sure you always remember what section you are in, and other than that, that's all the identifying factors. If you do this wrong, or if you're in a wrong exam room, your grade's going to be in later, like around a week or two, and it's just going to be a whole entire mess that you don't want to do. So make sure you have all of those logistics and that information for where you're taking the exam, what your student ID number is now, before you find out. All right. So before I would do this exam, I recommended some people who came to my office hours about this little tip that I used for exam one. So when you get this exam information sheet, I would start annotating it with our quantum numbers. This is one of the most missed topic on exam one, and it's not because it's a very memorization heavy thing. It's mostly just because people confuse things for other things. So to alleviate that, I recommend just writing down a couple of charts, specifically just writing down the symbols N, L, ML, and MS. Kind of make a table format here. So this is symbol, meaning. So N, that's our principal quantum number, and usually that means the size / energy. L, that's our shape of the orbital. ML, that's going to be the orientation of the orbital. And MS, that's going to be the spin. All right, and then after that, I would also recommend adding allowed values. So for N, it's going to be anything from 0 to infinity. We never really deal with 0, so for the purposes of Gen Chem 1, you're going to see N always going to be 1 to infinity, but you can have an N of 0 to infinity. And then L is also going to be to 0 to n minus 1. There's a big misconception here that L is n minus 1. It's not. That is a single possibility. It is a range from 0 to whatever n minus 1 is. Then orientation, that's going to be negative L to positive L. And size, pick your poison. It's going to be plus 1/2 or negative 1/2. Cool. Now another big thing that we miss with quantum numbers is what L is and what that determines, or what specific L value determines what shape of orbital we have. So I also have a little chart here. 0, do L value and shape. 0, 1, and 2. Those are the only L values that you're required to know. Shape, or actually, I'm going to do symbol, then shape. Symbol, shape. 0's S, P, D. And we also talked about the F orbital, but we're not required to know what the shape or what L value that is. But if you're interested, it is 3 and F. Okay, so the shape for an S orbital, that's going to be a circle. For P, I like to think of it as a peanut. For D, that is going to be our 4-leaf clover. And for F, you don't need to know that. Cool. And also, we did talk about D having a pacifier orbital that kind of looks like a P orbital but has a little halo going around it. That's just a, just so you know, fact. You don't have to know this for this exam. Okay. And the purpose of memorizing these tables is whenever you get a quantum number question, you can refer to these tables that you written in the beginning of the exam, and basically, or theoretically, you should get them all right because you have all the information right in front of you. So how to do this? Route memorization. Just get a blank piece of paper and just keep drawing these tables until it basically matches what you see in your notes. You can add some extra information if you want to, but this is practically what I used for my first exam. Alrighty. Now, once you've done that, or if you're good with quantum numbers, you're ready to start the exam, I recommend starting with the free response questions. And the reason is because some people are slow exam takers, and that's okay. But if you're a person that goes to the time limit, don't let the time limit end when you're doing question 24, because there's no way to, like, I have 1 minute to figure out what's happening here and write down an answer. That is very stressful. That is going to be a recipe for disaster. Instead, I recommend starting with these questions, or even the short answer questions, any of these free response questions in general, and then going to the free response questions, because I would much rather prefer a 50% shot, not 50, 20% shot to get an answer right rather than, oh, I just have to write something for pity points. All right, so going with that strategy, let's start with question 20. Provide the atomic symbol for each element. You're just going to have to do route memorization. The requirement for Gen Chem 1 is elements 1 through 36. So let's just go through them. And usually these elements have a specific order or kind of theme. It's usually the first letter or the sound of the element. So nitrogen, N. Cool. Potassium, this is not intuitive, it is K. And I like thinking about it because I don't really like bananas, or I don't really like bananas, but I'm okay with them. So potassium, K. Copper, Cu. Manganese, Mn. Do not confuse it with magnesium, that is Mg. Okay, cool. That's just route memorization. That's just something you're going to have to use flashcards for, unfortunately. 21. Mrs. Black and Dr. Outlaw discovered a new element in lab. This element has 3 isotopes. As shown below, calculate the average atomic mass of this new element. Report your answer to the mass of atomic mass units to 4 sig figs. So this one, you don't have to show your work because it just is a short answer question, so only fill the blanks, but this one you will have to put in some work. And you're given a specific amount of isotopes and percent abundance. So when we're talking about isotopes, there are many isotopes within all the elements in the periodic table, and the only differentiating factor about these isotopes is the amount of neutrons. So some isotopes of boron may have 11 neutrons, while some isotopes of boron have 10 neutrons. And the average of how prevalent that is within a sample group, that is how they get this number here, average atomic mass. So using that principle, if we have a element that has 3 isotopes, all we need to do is multiply the mass number of that isotope times the percent abundance, and we'll get a number, and we would just have to add all those isotopes together to add to 100% of that sample, add those numbers together, and answer to 4 sig figs, and we should get the right answer. Make sure, report your answer in atomic mass units. Units are very important in chemistry. You have to write down the units. Whatever answer you get here and you just write it as a number, that means absolutely nothing without the units. So please write down the units. Alrighty. So for mass, AMU, that's 150 times 90%, which in the calculator, you should put as 0.9050, because that is the definition of a percentage. It's just you take the one that would be 100%, anything below that it would just be with after the decimal point. So to be 150 times 0.905, I got 135.75. Then for this one, this would be 0.063, so 148 times 0.063, I got 9.324. Then I have 150 times 0.032. 151 times 0.032. I get 4.832. And all I have to do is add these numbers up, and since the question says round to 4 sig figs, I'm not really worrying about the amount of sig figs that I have right now. I'm just going to add everything up in my calculator. Oops. Stand by. Alrighty, I got 149.906 as my answer without considering sig figs. And then considering sig figs, we have to round to our 4th sig fig, which would be the 10th place. There's nothing in the 100th place to round to, so it would just simply be 149.9. And remember, atomic mass units, so you put AMU. Cool. Moving on to question 22. A helium balloon contains 14 liters of helium gas. That's important for this problem at standard temperature and pressure. That's something that you'll go over in Gen Chem 2 if you have that class. Knowing that helium gas has a density of 1.79 decigrams per liter, that's another conversion factor. How many atoms of helium gas are in this balloon? Cool. So we're given a couple conversion factors, 14 liters of helium, and we're also given 1.79 grams of helium will be in a liter of helium. Cool. And as Dr. Outlaw said, for large dimensional analysis problems or word problems in general, start with the conversion factor that doesn't have a fraction. So for me, I'll start with 14 liters and see where we can go from. Decigrams, not grams. So 14 liters of helium. Now I see liters on the bottom, so I'm going to put liters on the bottom and see where that cancels out to. That is 1.79 decigrams of helium. Cool. So now we have everything in terms of decigrams. Now we covered a concept in class about the mole and what that means. So there's a relationship. You can convert grams to moles and vice versa, and then moles to atoms, or aka Avogadro's number. And it's important to note for this grams has to be specific to the identity of that element. You can't just pick a willy-nilly number. It has to be specific to the molar mass of that specific element or molecule. Okay, well, first order of business is to convert the decigrams into grams, and for that I will go to my exam information sheet and figure out what decigrams means. Cool. So deci means 10 to the negative 1. So when I see this, a lot of people are confusing decigram or just any of this conversion factors found in the exam information sheet and flip-flopping them. I see a lot of people just put 10 to the negative 1 decigrams is 1 gram. That is flip-flopped. The language here is 1 deci of any unit is 10 to the negative 1 of that unit. So replacing it, decigram, 1 decigram is 10 to the negative 1 gram. So let's flip-flop that to make sure that is correct. And if you want to think about it a different way, if you see a prefix like deci, milli, kilo, femto, any prefix with a SI unit following right after it, that's where I would put the 1. Cool. Right after that, we got grams. Now we can go use this relationship between grams, moles, and number of atoms using the periodic table. So to do this, we'll use the molecular or molar mass of that element and convert it to moles. So 1 mole of helium is going to be this many grams of helium. Let me look at the 4.003 grams of helium will be 1 mole of helium. That is what this number is saying here. Scrolling back down. 4.003 grams of helium is 1 mole of helium. And simply converting from moles to atoms, I don't think anyone's having significant issues with this. Definition of a mole is 6.22 times 10 to the 23rd and of anything. In this case, atoms. Ooh, running out of space here. Cool. So now we have all that done. Let's just double check our dimensional analysis and see if all of the units cancel out. So I already did that with helium, decigrams cancel out, grams cancel out, moles cancel out, and we're left with atoms. Is that what the question is asking? It is. So I have a tip for how to enter dimensional analysis in your calculator. You will just take all the numerators, and what I mean by numerators, all the things on the top, and just throw it in the calculator and multiply them by each other. So I'll take 14 times 1.79 times 10 to the negative 1 times Avogadro's number, 6.22 times 10 to the 23rd. I get 1.509 many numbers after times 10 to the 24th. Then I'll take that number, save it in my calculator. Then I'll take all the numbers on the denominator or the bottom line, multiply them all together, and take the numerator divided by the denominator. And doing this will avoid all the time spent accurately entering in all the fractions. It also, for me, is a more safe way of computing everything. So you don't have to worry about, just fat thumbing it or the calculator being weird, because some people's calculators, in my experience, have been being weird this semester. All right. I get 3 point, all this equals out to 3.7699, goes on for a hot minute, times 10 to the 23rd atoms of helium. Remember, we have to report all of our work in sig figs. So let's go over them. 14 liters of helium, that's 2 sig figs, that is measured. This density, that's 3 sig figs, measured. This is infinite sig figs. The definition of decigrams is 10 to the negative 1 grams. This is going to be measured on the bottom, 4.003 grams of helium. That's 4 sig figs. And this is also 4 sig figs. So multiplication division rule states that whatever number is the lowest sig figs in the series of multiplication and division, that is going to be what we round our answer to. And since I see 2, that's the lowest number, I'm going to round my answer to 3.8 times 10 to the 23rd. This is important. Atoms of helium. Now, I cannot stress, first, box your answers so Dr. Outlaw has a easier time finding your answer, because sometimes, I understand this, you go through a lot of frameworks of how you solve this issue or problem, and it kind of looks like chicken scratch at the end. So just box in your answer so it's more clear to Dr. Outlaw or whoever is grading this exam that that's the answer. And just as how this is going to be graded, please show all of your work. If you don't show all of your work and you just write 3.8 times 10 to the 23 atoms of helium, you're not getting that 10 full points. You have to show your work, have to show your reasoning, and demonstrate that you can do the work as well as get the right answer. And on the flip side, if you don't know what to do, please put your genuine effort, because if you don't put anything, there's nothing to grade, 0 points. If you give it your best shot, maybe there is some chance you're on the right track, but you just deviated somewhere, so that might be half points or 3/4 points. Just to throw that out there. All right, last free response question. Calculate the total energy in kilojoules of a mole of photons with a wavelength of 82 nanometers. One sentence with a lot of information. So what I see here is wavelength, 82 nanometers. I see energy in a mole of photons. So how can we convert this in normal everyday language? By using the exam information sheet, let's look at what relationship we have talked about that talks about wavelength, energy, and maybe photons. Look at this. I see energy, I see wavelength. This is probably the equation that I should use. And what I'm demonstrating here is, when in doubt, look at your equations in the exam information sheet. Maybe there's something that you can find that's going to be useful for the equation, or that's necessary to find the answer. Equation we're going to be using is E equals hc over lambda. And lambda is wavelength. Cool. Now it's important to note, this mole of photons, each photon has a wavelength of 82 nanometers. The entire mole doesn't have 82 nanometers, just one photon of that mole. So whenever we're computing energy from this formula, that's just going to be the energy of one photon, not a mole of photons. So to kind of derive this and to better, more accurate information to what's happening to the problem, I would put E sub photon equals Planck's constant, which you can find on the exam information sheet. I'm going to look at that real quick. 6.63 times 10 to the negative 134? Negative 34 joules times second. Cool. Now we have the speed of light, 3.00 times 10 to the 8th meters per second, all over wavelength. Now, look at this, nanometers, meters. Convert this into meters, please, because if you just throw 82 nanometers, the units will not cancel out correctly. So let's do that on the side. Let's choose blue. 82.0 nanometers. Nanometers have to go on the bottom, and as I just said, to reiterate, the 1 goes with the the 1 goes with the prefix 10 to the power of, I believe, 9? Negative 9, close. 10 to the power of negative 9, that goes with the base unit. Cool, nanometers cancel out into meters, so that's going to be 8.2 times 10 to the negative 8 meters. Throw that bad boy in here. Cool. So now we have all the numbers to solve for energy of photon. Let's double check all the units and make sure it cancels out to a unit of energy, aka joules. Okay, well, I see seconds right here. Well, actually, let's go over that a little bit later. I see meters on the bottom, meters on the top. That cancels out, cool. And now some of you say that, or I've seen some people confuse that this second right here and this second right here will times to get second squared. Realize this second is getting multiplied on the numerator, while this second right here, that is already on the divided side. It's on the denominator. So in fact, this is getting canceled out. So all we're left with is joules. Joules is a unit of energy, so I'm going to continue on with my math and do that little quick trick and see, hey, this is multiplying the numerators divided by denominators, and I should get the right answer. Now, when you're doing stuff with multiple components in the denominator, make sure you just put a parentheses around this, because if you don't, you are going to get the wrong answer because you are dividing by 8.2, then you're going to times it by 10 to the negative 8, which is not what we're doing. We are having that entire expression here divide whatever is in the numerator. Okay, so I get a lot of numbers here. I'm just going to save it in the calculator, and I'm going to write, I don't know, let's say up to here. Goes on for a hot minute times 10 to the negative 18th joules. Now reminder, this is the energy for one photon, not a mole of photons. Also, let's keep track of sig figs here. I get 3 sig figs here. This is measured, measured, measured. So whatever this answer is going to be, it's going to be rounded to, oh, nope, sorry. This is going to be 3 sig figs, because we were given this in 3 sig figs. That is my mistake. So this answer is going to be rounded to 3 sig figs. Do not round until the very last step. I'm just keeping track of sig figs, so whenever we do have to round for sig figs, it's a little bit more clear what we have to do. Cool. So now we have this amount of energy for 1 photon. Let's calculate the energy in kilojoules of a mole of photons. So in all reality, what that's saying is get your answer in kilojoules per mole. Alrighty. So how do we do this? As I already said, what we just calculated, this is going to be the energy of 1 photon. Or in human language, it's going to be this amount of joules per photon. Now, I think the easiest way to do this is convert kilojoules to joules. Sorry, opposite way, joules to kilojoules. So 10 to the third joules as 1 kilojoule. Now, remember, we want to cancel out photons here on the bottom. So what we're going to do is 6.022, or Avogadro's number of photons, is 1 mole of photon. Or I'm just going to put 1 mole because that's more in the language of kilojoules per mole. Cool. So let's cancel out and see if we get our answer into the language of kilojoules per mole. Joules cancel out. We're left with kilojoules. Photons cancel out. Nice. We're left with kilojoules per mole. Throw that bad boy in the calculator. And make sure to save this number into its entirety for your calculations. Then divide it by what's ever happening in the bottom. That's just 10 to the third. I get 1,460.7, goes on for a while, kilojoules per mole. And then let's go over sig figs. As we already determined, this is going to be rounded to 3 sig figs. This is infinite over here because this is true by definition, and this is 4 sig figs. Rules of multiplication and division, whatever is the lowest amount of sig figs is what we're going to round to. So this answer is going to be rounded to 3 sig figs, or simply 1460 kilojoules per mole. Cool. And make sure to box your answer if you have a lot of work going on here, because it's more clear to Dr. Outlaw what your answer is. Cool. Now we spent our bulk of our time doing those free response questions, and all we have left is multiple choice, which is less weighted. I want to emphasize this is less weighted than all these questions down here. 4 points, 2 points, 10 points, 8 points. So make sure to get these first, not only because they're free response questions and if you run out of time on them, you're kind of cooked, but also for the fact that they are worth more points. So spend that extra time, get those points, and spend less time, spend an adequate amount of time, not too much time, for these multiple choice questions. Alrighty, let's dive into this. Question 1, which quantity has the greatest number of sig figs? This is going to be looking at each answer choice, seeing which one's more. I see 2 sig figs here. Anything trailing after that doesn't have a decimal point at the end, that is not significant. So this only has 2. This one, leading zeros are never significant. This only has 2. Trailing zeros, that's after a decimal point or has a decimal point, that is significant. So this is 4. Again, doesn't have a decimal point over here, so that trailing 0, that's insignificant. And then opposite here, this trailing 0 is after or has a decimal point, so that's significant. The one that's largest is answer choice C. Cool. Select the true statement based on the mass spec below. So we have two isotopes, isotope 803 and isotope 805, with a specific mass. So this is going to be in percent abundance. So we can already tell by just this graph, not even looking at the answer choices, that isotope 803, that's going to be the isotope that is more prevalent within our sample. Cool. So answer choice A, that says the average atomic mass of this element would be 804 AMU. I don't think we can calculate this just based on these two isotopes are in different percent abundances. If it was 50-50, that would be plausible for the average atomic mass to be 804. But since it's uneven, we cannot say for entire certainty that this is true. B, all atoms of this element have 803 or 805 protons. Now, logically, this does not make sense. Let's look at the periodic table. We go all the way to 118 protons. So that doesn't make sense, but to break it down, the mass of any isotope is comprised of two things: the protons and the neutrons. Now, the reason why we don't include electrons in this mass count is because they're so small that for general chemistry and for most chemists in general, we just consider that insignificant. So B, wrong. 3, the heavier isotope of this element is the most common isotope. We can just look at this by the mass of AMU. 803 is more common and has the least weight, so that's wrong. D, the least abundant isotope has the most neutrons. Remember, each isotope of an element, the definition of the element is how many protons you have. So isotope 803 and isotope 805 both have the same amount of protons. The only thing that differs them is the amount of neutrons. So this is in fact true because 805 has more neutrons and is less abundant. But let's just look at answer choice E. The average atomic mass of this element will be between 804 and 805. I would disagree. I would say between 804 and 803, just because the abundance of isotope 803 is more prevalent than 805. So if we were to draw a line, this is 804, it would fall roughly around here. This is just a guess, but it's not between 804 and 805. Now, if it was opposite, where 803 was here and 805 was here, then I would say it's plausible that 804 and 805 is roughly the range that we're looking for the average atomic mass of this isotope. Cool. Question 3. If I can run 10 kilometers in an hour, how many meters can I run in a day if I continue running at the same pace? Cool. So we're starting 10 kilometers an hour. And we're trying to find how much we can do within a day. So remember, let's convert our hours to days because that is a unit of time. A definition of hour, or a definition of a day, is 24 hours. And a definition of a kilometer via your exam information sheet, 1 kilometer is 10 to the third meters. If I run 10 kilometers, how many meters I can run in a day? Meters per day. That's what the language we're trying to get into. So let's make sure that cancels out. We're left with days, meters, cool. So I'm just going to throw that in my calculator, see what I get. 10 times 24 times 10 to the third. I get 2 times 10 to the fifth. Cool. Keep going on. How many cubic yards are equivalent to 1.83 times 8 inches cubed? 1 yard is exactly equal to 36 inches. The language exactly means that's true by definition, aka infinite sig figs. But since it's a multiple choice question and it doesn't have different answer choices in sig figs, this won't be a very important part to the problem, but it's good to know if this was a free response question. So we're given in inches cubed. Now to cancel out inches just normally, not considering the cubes, we would put inches on the bottom and yards on the top. And the question says 1 yard is 36 inches exactly. The only thing that we have to do is we have to repeat this 3 times because it's 2 to the third. And the way we can do this is either you can write that conversion factor 1 yard per 36 inches 3 times, or you can write an exponent of 3 to denote that you did that function 3 times. After that, all of the inches cubed would be canceled out, and you would be left with yards, cubic yards. So let's put that in the calculator. 168.3 divided by 36 cubed. Remember, just because we canceled out the units does not mean we can ignore the exponent for the actual number that goes with the unit. If you put an exponent on the outside of the parentheses, it goes to every single portion that's encompassing that parentheses. So for that, I get answer choice B, which is 3.607 times 10 to the 3. It has a lot of numbers after that, but it roughly rounds to that scientific notation. Cool. Sample of metal is cooked, that it shrinks. What is the true density of that metal at the lower temperature? So remember, 2 parts of density. We have the volume that it occupies and the grams, or not grams, the mass that it takes. Usually you'll see density in grams per milliliter. You can also see in kilograms per liter. Any unit of mass over volume, that is density. So when we're talking about a sample of metal is cooled, that it shrinks, that is referring to its volume. So if we have mass and volume, this is going to be great. This is before cooling, by the way. And then we cool it. Let's say the volume shrinks by half of the volume, but we maintain the same mass. Just because that volume shrinked, the true density of that metal has increased because the volume decreased. Remember, this is 1/2 of volume in a more expanded form. That means we times this entire thing by 2. So the density would be twice the amount if the volume shrunk by 1/2. Now, this isn't what exactly is happening. It isn't that extreme of an example, but the mass would definitely stay the same and the volume would decrease, resulting in an increase of density, aka answer choice D. Cool. Number 6, nuclei symbol with the same number of neutrons. That's important, but different numbers called isotones, not to be confused with isotopes. Which of the following nuclei is an isotone of this? Which is tin. Okay, just to go over a basic nuclei symbol, I'm going to denote X as our element. This is going to be AMU, which I just covered in question number 2, that AMU is protons plus neutrons. then this is going to be protons. So remember, we were just given the definition of an isotone. It is the same amount of neutrons. To figure that out, we just take AMU minus the amount of protons and make sure that equals 70, because that is 120 minus 50. Alrighty, let's go through each one. SB, 120 minus 51, 69, nope. 122 minus 52, that's 70. That might be our answer choice. I'm going to circle that right now. Let's look through all the other choices. IN minus 66, 49, answer choice C, nope. 120 minus 54, 66, nope. Answer choice B is our correct answer. Going on, which of the following statements regarding sodium and beryllium is true? Answer choice A says 1 gram of beryllium consists of fewer atoms than 1 gram of sodium. The way that you can figure this out is by looking at the periodic table and converting grams to moles. So you don't have to do all the math for this. Let's circle beryllium and let's circle sodium. We have 1 gram of each. If you divide each by whatever number that is on the bottom, that will be how many moles that is. And remember, moles is all universal because the definition of mole is always Avogadro's number. Converting from grams to moles, that's going to be unique to the identity of that element and or molecule. Since beryllium has 9.012 grams per mole, that is going to result in more moles being made, aka answer choice A would actually make beryllium, this 1 gram of beryllium would have more atoms than sodium. Cool, answer choice B. 1 mole of beryllium has the same number of atoms as 1 mole of sodium. Just to reiterate, a mole of anything is universal. Definition of mole is Avogadro's number. So if we're converting moles to atoms, it's always going to be 6.022 times 10 to the 23rd moles, or atoms per mole in this case. So answer choice B, I'm going to say that that's right for now, but let's look at all the other answer choices. 1 mole of beryllium consists of more atoms than 1 mole of sodium. Just because of what we just said in B, this has to be wrong. 1 mole of beryllium has the same mass as 1 mole of sodium. Remember, I just said that to get the amount of moles, it would have to consist of different amounts of grams, because converting from grams to moles, that is going to be different for each unique element and or molecule. For E, 1 mole of beryllium has more protons than 1 mole of sodium. Let's look at that. So beryllium, that will have 4 protons, and sodium will have 11 protons. Times that by Avogadro's number, sodium should have 11 times more protons than beryllium. So it doesn't matter that we threw a mole in there. Beryllium has less protons by definition, and a mole is always 6.022 times 10 to the 23rd. So answer choice E does not make sense. Cool. In which of the following pairs is the heavier isotope the most abundant isotope? I'm going to take a little screenshot of these answers, and we're going to go right back to our handy dandy periodic table. Alrighty. So just to unpack this, if I had the heavier isotope, let's just say for boron, let's say we have boron 11 and boron 10? We see that the average atomic mass is 10.86, so that is telling me that between these two isotopes, boron 11 is going to be heavier just because that number, or that average between the two, is closer to 11 rather than 10. Using that same principle, let's look at all the other answer choices. Helium, that is 1.008. Nope. The first element is, or first isotope is more abundant. Let's look at B, neon, 20.18. That is very close to that first option. Nope. C, nitrogen 14 and nitrogen 15. 14.01 for nitrogen. That's the average. That's very close to 14. For IN, over here, it's 114.8. So we have isotope 113 and 115. 114.8 is much closer to 115. So our answer would be D. But let's look at answer choice E to make sure. Antimony, 121.8. That's closer to 121 than 123. So this is not the answer. My fault. Okay. Answer choice D. Number 9. The number situated above the chemical symbol in the periodic table entry to the right represents the atomic number. That's just straight out of your notes. And atomic number, that is also the same as protons, number of protons. Mass number, nope. We already talked about it. That's not mass number, that's atomic number, that's protons. Number of neutrons, nope. Average atomic mass, nope. Isotope, nope. That's just what this number is up here. Which of the following statements is true? The nucleus takes up the majority of the space in an atom. That is not true. When we talk about the model of an atom, the nucleus takes up a sizable part, but these electrons are so far away that the entire volume of that atom is mostly comprised of the space that the electrons take. Actually, I'm going to keep that up there for reference. Question or statement number 2, protons and neutrons have approximately the same mass. I'm going to say that is true. And the reason is how we determine AMU. Remember, it is protons plus neutrons and we weight them equally. They're a little bit different, but for the purposes of this class, they are practically the same. Now, electrons, that is not equal. They are so small and so light that they're negligible for the mass of an atom. Statement number 3, protons and electrons are found in a nucleus. No, that's just protons and neutrons. And so answer choice B is our correct option. Number 11, which of the following statements about isotopes are false? So statement A, isotopes are two atoms of the same element. That is true. Remember, isotopes, there are two atoms of the same element, and the only thing that's different is the amount of neutrons. Answer choice B, isotopes have the same atomic number. That's basically the same thing as answer choice A. Isotopes of the same element have a different number of neutrons. Again, definition of isotopes, same element, different amount of neutrons. Answer choice B, isotopes of the same element have the same nuclide symbol. That is false. Remember, nuclide symbol, this is going to be AMU and number of protons. So these two components, the symbol and the amount of protons, that's going to stay consistent. However, the AMU, that is composed of both protons and neutrons. And since the isotopes have different amounts of neutrons, that mass number is not going to be consistent. So answer choice D, they would have different nuclide symbols. In E, isotopes have the same number of electrons. That will be true. Cool. What is the nuclide symbol for an atom of bromine with 44 neutrons? So, cool. First off, bromine is one of the things that we just learned. So any of the B, which is boron, that's automatically wrong. So we're already left with two answer choices. And remember, we don't even have to compute the amount of protons here, because look, we're given 44 neutrons. I see 44 on the bottom where protons should be. This answer choice is automatically wrong. And it should be answer choice A, but let's confirm that. So 44 plus whatever the amount of protons boron has, or not boron, bromine has, and that should be the weight, or AMU that's on the top. So 44 plus 35 is 79. Let's look at that number again, 79, cool. How many atoms of tin are there in 2 millimole of tin? Now this isn't a typo, this is millimole. So first let's convert this to moles. In 1 millimole, there's going to be 10 to the negative 3 moles. Then we're going to times this by Avogadro's number. Definition of a mole is 6.022 times 10 to the 23rd. Everything cancels out, millimoles, millimoles, moles, moles, all into atoms. So 2 times 10 to the negative 3rd times Avogadro's number should be our answer. Put that in a calculator real quick. I get answer choice B. And look at answer choice A. Make sure you keep your negatives, because if you did not keep that negative, you would have gotten the answer choice A. Cool. How many moles of copper are in 5.6 grams of solid copper? That is just going straight to our periodic table, looking at how much grams per mole is copper and using that to convert it into moles. So we got 5.6 grams of copper. In each mole of copper, there should be 63.55 grams of copper per mole. So dimensional analysis way to put this down. In 63.55 grams of copper, there's 1 mole of copper. So it's basically just 5.6 divided by 63.55. I got 0.88 moles. That's answer choice A. Cool. Change from n equals 7 to n equals 5 involves blank energy and a photon of blank wavelength. Then a change from n3 to n equals 5. Let's just recap what this orbital energy diagram looks like. So it has a big up arrow, E is here, and it has each of our n principal quantum numbers labeled out. I'm going to do that. And the very big thing you need to know about here is the change between each jump in principal quantum number. It gets smaller. So this is 1, 2, 3, 4, 5, 6, and 7. So you realize the gap between 1 and 2 is much larger of a change in energy than 7 and 6. Cool. So if we're looking at that, our little gram, the jump from 7 to 5, that's a pretty small distance. But compare it to 3 to 5, that's a still small difference, but it's a sizable change. So it's going to be a lesser change in energy. And also, remember, with the equation of E equals h frequency times hc over lambda. This is a mathematical way to say that if we increase energy, we increase frequency, and we decrease wavelength. You see how wavelength, or lambda, is on the bottom? That says it's inversely proportional. And the opposite's true. A shorter energy, or not shorter, less energy, or a less energy change is predictive of less frequency and longer wavelength. Applying that to that problem, if we have a less energy change, it should have a longer wavelength, which is answer choice A. Question 16, which of the following statements is true? Let's look at them. Statement A says any orbital can hold a maximum of 2 electrons of opposite spin. That's going to be true. I'm going to dive into why that's right with our little chart, but let's go through all the other options to make sure that we just did not select the wrong answer. So answer choice B says a maximum of 6 electrons can fill the n equals 2 energy state. So I'm going to look at our little table here, and this is an exercise that we did inside a class. So if we have n equals 2, our allowed L values will be 0 and 1, because it goes from a range from 0 to n minus 1. So 0 and 1. And ml of that is going to be positive to negative L. So 0, and this will be negative 1, 0, and positive 1. And within each orientation of ml, they can fit an electron of upspin and downspin, or positive 1/2 and negative 1/2. So this is 2. This also has upspin, downspin, upspin, downspin, upspin, and downspin. So in total, we have 8 electrons. Answer choice B says 6, so that is incorrect. An F subshell has an L of 4. We just went over this in our little handy dandy chart that you should probably have put into your exam information sheet when this started. L value of 3, that designates a symbol of F. Wrong. D, the S subshell only occurs in n equals 1. Remember, I said this in the beginning. Just because L can have a range of 0 to n minus 1 does not mean that it has to be n minus 1. So if we had a principal quantum number, let's say 3, n equals 3, L can be anywhere from 0 to n minus 1, in this case would be 2. So L can be 0, 1, and 2. And that's very proven in how we organize the periodic table, as we just gone over in class. Going back over here, this is our n equals 3, or period 3. This is our S block right here. So this would be 3s, or 3, and this is an L value of 0. This is an L value of 1. And then this is also in the principal quantum number of 3, but it's down here. We'll go into why a little bit later in our next lectures. So just because the principal quantum number is 3 does not mean the L value has to be n minus 1. Answer choice C, nope. The values of ml for p subshell are -2, 1, 0, +1, and -2. Remember, using that little chart, if we have a p subshell, that correlates to an L value of 1. And if we're looking at the mLs, going back here, sorry, if we have an L of 1, the mLs will be -L to +L. So -1, 0, and +1, not -2, -1, 0, 1, and 2. So answer choice E is wrong, so process and elimination says answer choice A is right. And as I reiterated for answer choice B, a maximum of 6 electrons can fill the n2 energy states in each orbital. It's just factual that an orbital will hold an upspin and a downspin electron. Cool. And question 17, we're almost at the end of this. What are the possible L values for the orbital shown? This is a d orbital, and that correlates to an L value of 2. So possible ML will be negative L to positive L. So that will be negative 2 to positive 2, which is answer choice E. And again, I'm not going to go all the way down to the little table that we just drew. Just imagine you looked at that table and got that information from there, or if you have it memorized, more power to you. Which of the following sets of quantum numbers is not allowed? So let's just go this by answer choice by answer choice. Answer choice A, we have a principal quantum number, or principal number of 1, and L, that is 2. That fulfills that n-1 rule, so that's cool. ML, that's also 0, so that follows that rule for determining ML, and it has a 1/2 or negative 1/2, so this is allowed. And then same reason for B, that L value fulfills that allowed range of 0 to n-1, as well as the ML rule of going from negative L to positive L. Now, answer choice C. Big numbers, but let's still use what we know of allowed values. Principal quantum number goes from 0 to infinity. That checks out. 24. 15 is our L value, and remember it goes from 0 to n-1. So in this case it would go from 0 to 23. That's allowed. Then, since our L is 15, it would go from negative 15 to positive 15 for ML, so that's allowed, and it has a 1/2 at the end, so that's allowed. Answer choice D, same thing that's we gone over, principal quantum number 0 to infinity, that's true. This is n-1. This is in that range of negative L to positive L and has that 1/2. And now this one, by process of elimination, has to be this one. But look, the principal quantum number and the L value is the same. Remember, our n-1 rule for L has to be arranged from 0 to n-1. So if we have a principal quantum number of 3, it will be 0 to 2. Since we have an L value of 3, that makes absolutely no sense. Cool. Number 19. This is a question that I remember. I'm pretty sure this was an exam question from last semester. The biggest trick was not finding the frequency or using that equation on your exam information sheet, but realizing that this 2 millimeters, that's not the wavelength. That is the wavelength of a couple of wavelengths. So this wavelength plus this wavelength plus this wavelength plus this wavelength. So that 2 millimeters is actually 4 different wavelengths added to each other. So what do we do about that? Since we have 4 wavelengths encompassing this wave and we have a designated distance, divided by 4 because there's 4. So 2 divided by 4, that is 0.5, 0.5 millimeter. Now, we are trying to relate the wavelength to the frequency of light. And how are we going to do that? Let's look at our exam information sheet and find a relevant relationship. I will use the relationship HV equals HC over lambda because I relate frequency and what we're looking for, or wavelength and what we're looking for. So HV equals HC divided by lambda. And before you even do this, let's cancel out. Sorry, you can use another, these two relationships. This one and this relationship can both work for this. I was just about to say you can divide by Planck's constant and divide that to find out frequency, but you can also rearrange this to find frequency, so it would be C divided by lambda equals frequency. So this, you can go that way, or this, you can, or C equals frequency times wavelength, you can go that way. There's two options here, and each are equally as correct. Since I already started like that, I'm just going to keep it pushing. All divided by Planck's constant, so that cancels out Planck's constant. So now we're left with frequency equals hc, or 8, c divided by lambda. Cool. Now we just substitute our values in and realize speed of light is in meters per second, so we will have to convert that in, what am I doing? That is not the speed of light. Divided by, let's convert that, 1 millimeter is 10 to the negative 3 meters. I get 5 times 10 to the negative 4 meters. Meters cancel out. And frequency is going to be in terms of 1 over seconds. And remember, 1 over seconds, if you don't know what that is, it's in your exam information sheet. It's very informative. 1 hertz is 1 second to the negative 1, which is the same thing as just saying 1 over second. Where is it? Right here. Cool. Now we just take these two numerators and divide them by each other. And you should get answer choice, well, I get answer choice E, because it rounds to 1 sig fig. Cool. So that is every single question broken down. If you have any other questions, please come to my office hours or email me. Those office hours and location for that is found on the syllabus. And if it does change for office hours, I will make a Canvas announcement detailing what's happening there. But other than that, have a great night and good luck studying for this exam. Thank you.